All right, today we're going to trace a pretty fascinating line. It starts with an old philosophical debate about the nature of infinity and ends, believe it or not, with the actual code running on your computer right now.
So let me start by asking you a kind of strange question. What if a math proof wasn't just some static argument written on a page? What if it was actually something you could run, a dynamic executable process? What if proving something existed was the same thing as actually building it? Now, this isn't science fiction. It's the core idea behind a really powerful field of mathematics.
To really get how we connect proofs to programs, we first have to jump back in time, way back, to a fundamental disagreement about what infinity even is.
So, you basically had two camps. On one side, you have the classical view, with guys like George Cantor. For him, you could prove something exists just by showing that it not existing would lead to a logical contradiction, a paradox. He was totally comfortable with this idea of actual infinity, treating an infinite set, like all the whole numbers, as one single completed thing. But on the other side, you had thinkers like Leibniz, and they had a totally different take. For them, an object exists only if you can give me a concrete recipe for building it. They were really skeptical of treating infinity like some whole thing you could just hold in your hand.
And this quote from Leibniz really hits the nail on the head. He's basically saying, sure, you can talk about a process that goes on forever, but you can't just talk about the completed result of that infinite process like it's a finished object. You can't assign a number to an infinite collection. It's just not a thing.
And this gets us right to the heart of the matter, the real philosophical showdown. Is it enough to just prove that something must exist through some clever logical trick? Or do you have to actually roll up your sleeves and provide the blueprint? Do you have to show me the thing?
That second attitude, that show me approach, well, that is the absolute foundation of constructive mathematics, and it plays by a completely different set of rules.
You see, in constructive math, a proof of existence isn't just a clever argument. It's a recipe. It has to be a method, an algorithm, a set of instructions that, if you actually follow them, will produce the mathematical object you're talking about. No recipe, no proof. It is that simple.
And this lays out the difference perfectly, doesn't it? The classical approach, that's your proof by contradiction. You assume the thing you want to prove is false, show that leads to some logical nonsense, and then you just declare victory. You've proven the thing exists, but you're left completely empty-handed. The constructive approach, though, is direct. You want to prove a number with some special property exists? Fine. Here's the algorithm to calculate it. The algorithm is the proof.
This way of thinking was really pushed forward in the 20th century by mathematicians like Bishop. This guy basically rebuilt a huge chunk of mathematics on purely constructive ground. He realized that if you focus on functions and algorithms, things you can actually compute, instead of vague, abstract sets, you build a type of mathematics that is computational from its very core.
Now, this intense focus on process and construction, it had this completely revolutionary side effect. It forced mathematicians to look at proofs themselves in a totally new light, not just as arguments, but as objects with their own internal structure. And this is the world of proof theory. Think of it like the mechanics of logic. Proof theorists take a proof, they pop the hood, and they break it down into its smallest logical steps to analyze its structure. It's kind of like an engineer analyzing a blueprint. They're literally studying the shape of an argument.
So when these proof theorists started analyzing the structure of these new constructive proofs, these step-by-step recipes for building things, they noticed something pretty incredible. They looked exactly like computer algorithms. The logical steps of the proof were a perfect mirror of the computational steps of a program. A proof that constructs a number looks just like a program that computes that number. And that was the moment everything changed.
This discovery wasn't just some cute analogy either. It turned into one of the most powerful and productive ideas connecting the worlds of pure mathematics and computer science.
So this brings us to the absolute key takeaway here. A constructive proof isn't just like a program. In a very deep, very formal sense, a constructive proof is a program, and a program is a proof. They're just two sides of the very same coin.
This profound connection has a formal name. It's called the Curry-Howard correspondence, or sometimes just the proofs as programs paradigm. What it does is establish a direct one-to-one link. So a mathematical statement, or a proposition, corresponds to a type in a programming language. And the proof of that proposition? That corresponds to a program that produces a value of that type.
This little dictionary here makes it crystal clear. In logic, you have a proposition, right? like there exists a prime number greater than 100. In programming, that's a type. We could call it prime greater than 100. The proof in logic is the program. So your proof would be an actual piece of code that finds a prime, like, say, 101. And get this, checking for logical consistency in the proof is the exact same process as a compiler type-checking your program to make sure it's sound.
And this isn't just some theoretical curiosity. It has massive real-world applications. So why does this matter? Well, because if a proof is a program, you can write software that is provably correct. For mission-critical systems in aviation or finance, that's an absolute game changer. It's the foundation for these incredible tools called interactive proof assistants, like Coq or Nupril, that let engineers and mathematicians build systems that are correct by their very construction. This idea has fundamentally shaped the design of modern programming languages that save all of us from countless bugs every single day.
So this whole journey, from Leibniz's philosophy of infinity all the way to the code that secures our digital world, it shows this deep, really beautiful unity between abstract thought and concrete technology. And it leaves us with a pretty compelling question. As this powerful merger of proving and computing continues to get stronger, what new, complex realities will we be able to not just imagine, but verifiably build?